Okay, so this is the May 265 Fall 2022 Midterm 1. In this first problem, we have these two matrices A and B, and we're also given that C is equal to A times the inverse of B, which gives us this matrix here. And we want to find the summation of all the entries in A times B inverse. So the first thing we need to do is find B inverse, and I think there's a formula for this that's pretty simple for a 2x2 matrix, but I kind of forget what that is, so I'm just going to calculate B inverse another way. And one of the ways to do this is by putting the matrix you want to take the inverse of on the left hand side, and then put the identity matrix on the right. So this is B, this is the identity matrix. And then you can row reduce, and what you end up wanting is some matrix in the form of this side being the identity matrix, and this side is going to be the inverse of whatever matrix you want to find the inverse of. So when we row reduce, we can first do second row is subtract the first row. And that will give us 1, 0, negative 1, 1. And then so we'll first do this row operation, and then afterwards we'll do row 1 is equal to row 1 minus 3 times row 2, where row 2 is now this new row. And when we do that, we get 0, 1, 4, and negative 3. And then I'm going to rearrange that by swapping the first and second row, and that will give me negative 1, 1, 4, negative 3, which is going to be B inverse. So now we can just do this multiplication, and we get 1, 2, 3, 5 times negative 1, 1, 4, negative 3, which is equal to 7, negative 5, 17, and negative 12. Okay, and then when we add these together, so we add 7, negative 5, 17, negative 12, and you can see that gives us 7, which is the answer. Okay, so for number 2, we have this linear transformation from R3 to R3 with the standard matrix given here, and we want to find K such that L is 1 to 1. Oh, whoa. Okay, so what the standard matrix means is that this is the matrix that you multiply by some x in your initial vector space, which in this case is R3. And this will give us the resulting vector in R3 in this case. So the thing to know about 1-to-1 matrices is that, oh my, okay. I don't know why it's acting up. Anyways, for 1-to-1 matrices, you want to map one value in this initial vector space to a unique solution or unique vector in the second vector space. So you don't want to map, for example, one vector in this space you don't want to map multiple vectors in this space to a single vector in this space. And so in this case, when you have R3 to R3, this means that for your AX equals B, you want to be able to, if I draw it out like this, where, there's 3 entries on all these because this is an R3. What you want is to have all pivot columns. So in this case, 1, 0, 0, 0, 1, 0, 0, 0, 1. And why? So you basically want to be able to map every single vector in this original vector space, which is the same dimension as the other one, the one you want to map to. And so to do that, you need to have a unique solution for all of these resulting values. So this is why, for example, when you're doing your row reduction, you want something like this, so that you always have a solution, a unique solution, because this for example, if this is x1, x2, x3, this will tell you what x1 is, this will tell you what x2 is, and this will tell you what x3 is, which will mean that there is a solution, and a unique solution for all of these vectors. So because of that, we want to have our A matrix be able to be reduced to the identity matrix. So we can do that just by doing row reduction. So to do that, we can do row 1 equals row 1 minus 2, or row 2, which will give us 1, 0, 1, 0, 1. Oops. Yeah. And then on this one we can do, after this row operation, we can do row 3 equals row 3 minus 2 row 1, where row 1 is now this new row 1, 0, 1, and that will give us 0, 3, and k minus 2. Wait. Yeah. Okay, so then from here we can do row 3 equals row 3 minus 3 row 2. And this will give us 0, 0, and then k minus 5. So as you can see, the only way that this matrix cannot become the identity matrix is if k is equal to 5. And if k is equal to 5, then when you row reduce, you'll get this row of zeros. And if this is going to be your standard matrix, so if this is going to be your standard matrix, then you're going to have either no solution for this, or you're going to have infinitely many solutions because of this 0. So for example, this was 0, you'd have infinitely many. If it wasn't 0, you'd have no solution for certain values. And so, not for certain values, you just wouldn't have a solution. So in the event that it's 1-to-1, you want to have a unique solution, which is why we want this matrix to be able to be reduced to the identity matrix. And the only way that it cannot be reduced is if k is equal to 5. So when k is not equal to 5, you will get a unique solution for this transformation, and the transformation will be 1-to-1. Okay, so for this problem, we're asked about which statements are true. First statement is that if A is a singular matrix, then its last column must be a linear combination of the first 7 columns. So singular means that is another way of saying that the matrix is not invertible, and that means that there is not a unique solution for every AX equals B. And this means that there will be some linear dependence in the columns. So if this was invertible, you would have, linearly independent columns. So one, for example, something like this, where all the other entries are 0, but you have a diagonal of 1s, which are the pivot columns. But in this case, because it's singular, you're going to have some linear dependence. But the statement says that the last column must be a linear combination of the first 7, which doesn't really make sense, because the only requirement for a singular matrix is that the columns, at first it's not invertible, which means that it has a linear dependence in the columns. So it doesn't need to be the last column, it could be any other column. And so one counterexample that you might just kind of play around and come up with is maybe something like this, where you have 1 and then 0 to 0, etc. And, you know, your other zeros. But then maybe you have a row of just zeros. And then say you have, your last column being this. And let's just assume, for simplicity of writing, that it's just a 4x4 matrix, actually. So in this case, you can see that this last column is not a linear combination of these three. It cannot be written as such. And so the statement is not true, because this is a good counterexample for it. In the second statement, we have let A be a 5x7 matrix such that AX equal B is consistent. And so this means that, you know, there is a solution for all B. Ooh, what is going on? Okay, I don't know what's going on. Okay, so there is a solution for B in R to the 5. And same thing for B, except it's a 7x11 matrix. Then the matrix equation A times AB times X equals B is consistent for all B in R to the 5. So if we look at this expression here, from our, is it associative? Okay, well, it's one of the properties, but I think it's associative. But if you have, say, like a matrix AB times C, you can write it's equivalent to A times BC. So in this case, we can write A times BX, A times B times X as A times BX. And we know that BX times BX equals C is consistent for all C. So this means that we have A times C, and we know that A times C is consistent for any B in R to the 5, and so this means that overall this system will be consistent for all B in R to the 5. And you can also double check these dimensions. So for example, if you have 5x7, okay, so let's just compare this one. So for example, 5x7 times B, which is a 7x11, which will give you a 5x11 matrix. And then your X is going to be to get a consistency for B and R to the 5. So this is a 5x1. So your X needs to be an 11x1 matrix. This is just a sanity check for dimensions to make sure that we're able to do what we just did with this multiplication here. So this means that X is an 11x1 matrix. So now we can also check for this case. So A times BX. So first BX is going to be 7x11 times what we just found, which is 11x1. And then we multiply, so this becomes a 7x1 matrix. And then we multiply by A, which is a 5x7 matrix. And that gives us a 5x1 matrix. And that makes sense, right? This is what B is going to be. So our sanity checks works, and so this is a true statement based on the associative property. In part 3, we have, for any m by n matrix A, the dimension of the null space equals the dimension of the null space of its transpose. So first of all, this kind of reminds me, well, whenever I see dimension of the null space, I think of the nullity. Well, because that's what it is, but that also makes me think of the rank nullity theorem, where you have the rank of A plus the nullity of A equals the number of columns, which in this case for A would be n. And then you can also write this for A transpose, rank times A transpose plus nullity times A transpose equals m, because when the transpose has m columns. So one of the properties of transpose is that the ranks are the same. So the rank of A is equal to the rank of the transpose of A. And from this, you can see that if the ranks are equal, then the dimension only, so the nullity of A only equals the nullity of A transpose when n and m are equal. But that might not be the case because this is just a random m by n matrix. So when n and m are not equal, then your nullities are not going to be equal. And so this statement is false. Finally, we have the statement, if A is an m by n matrix, then the set AX is a subspace of R to the m. And so, in this case, this probably does make sense. So, if you have this m by n matrix, then you want some x matrix, right? X is going to be a n by 1 matrix, and that's going to give you m times n times n by 1, n by 1 matrix. So just to be clear, I know it's like a multiplication sign, but I just mean like the dimensions of it here. So this will give you an m by 1 matrix. So that's going to be this, or vector, I guess is a better way of putting it. And so in this case, to satisfy the requirements of a subspace, right, you want to have the 0 vector inside the subspace, and then you also want it to be closed under addition and scalar multiplication. Okay, that's not very legible, but hopefully you get the gist. And so if we have this, we can see that if x is in the R to the n vector space, it is possible to have the 0 vector because x could just be 0. The other one is closed under addition. So if you have, for example, a times x1, if a times x1 is equal to a times x1 plus x2. And this is going to be the case just because this is a linear system, so there is no so it will be closed under under addition. Just based on the distributed property of these matrices. And so the other one that we need to check is scalar multiplication, which is fine because a times cx1 or a times cx equals c times ax, which makes sense because you just factor out the scalar because the equation is just ax, and so that is satisfied as well. And as a result, you can see that the resulting vector is an m by 1 matrix, which is in the subspace of Rn because it is satisfied by the 0 vector being in that subspace, so this could be 0. It's closed under addition, as we already shown over here, and it's also closed under scalar multiplication, which we have shown here. So this is a true statement. And this means our answer is D. Okay, so now we're trying to find the determinant of this matrix. And there's a lot of ways to do this. Some of them are harder than others. And the way that I think is easiest is if we do cofactor expansion. Cofactor expansion along this column. This is just going to be easier because all these are zeros, so you don't have to determine the determinant of all these other matrices after you've deleted rows and whatnot. So in this case, I like to think of this, I guess this is how I learned it, as a checkerboard, where these signs determine whether you add or subtract an element. So for example, because we're starting here with 2, that's a positive, so I just do plus 2 times the determinant of whatever's left. So, for example, though, if I started with -7, well, I would be doing -7, negative of -7, because this is where I'm starting from for that entry. But we're not doing that here. So we are starting with a positive. So +2 times, then we delete the column and row. Oh my goodness. Okay. So we're deleting the column and row of the original matrix and find the determinant of that, which gives us 0, 3, -4, -5, -8, 3, -6, 5, 0. And then we can do cofactor expansion along this row to find the determinant of this, because it's just, again, a lot easier because all your other entries are going to be 0. So again, we do checkerboard, and we start from the positives are always at the corners, and that's how you start going down the list. So I always start with the positive here and then just alternate. And here, so that means we have a negative here, so we have negative of -5 times, delete the column, delete the row, we get 3, -4, 5, -6, and that gives us 10 times -18 plus 20, which is 20. 20. So our answer is B. Okay, so in this one we're trying to find which of this following statements are always true. And, okay, first we have if A is an n by n matrix, then all entries are positive, then determinant of A is greater than 0. Honestly, for this, I think it's best to just try different things and come up with counterexamples, because it's pretty easy to come up with something, I think, and trying to rationalize it, in my opinion. But yeah, so obviously your entries are all positive, so if you have like A, B, C, D, A, D minus B, C is going to be your determinant, and you want this to be, the claim is that it's greater than 0 all the time. But what if, for example, you have like 1, 2, 2, 1? Well, this one's going to be 1 minus 4, which is going to be -3, which is less than 0. So this statement is false. The other is that if A and B are two n by n matrices with the determinant of A and determinant of B being greater than 0, then determinant of A plus B is greater than 0. So I don't know. I think coming up with counterexamples is a good way to just test things out. From this expression, it doesn't seem like there is a property that says the determinant of A plus B is equal to the determinant of A plus the determinant of B. That's not really a property that I've ever seen before, so I'm already a little questionable about it. So maybe I come up with counterexample again, and just I don't know. I think trying numbers is pretty helpful in these cases. So if you have, just say like the identity matrix. Oh my goodness. Okay. You have 1, 0, 0, 1. So let's say this is A. And then based on A, we kind of see that we want to have the B and C values be pretty big. So B, let's say that, okay. Sorry for these technical difficulties. I don't know what's going on. Okay, well, anyways. So let's say that B is equal to, like, well, it can't be 0. So we can't do something like 0, 5, 5, 0, because that would mean determinant of B is less than 0. I think we could try something like, well, actually, you could try something like negative. Okay, let's try something else. So you can also use negative numbers, obviously. So if we have, 0, 0 on these diagonals, but then we have maybe -4, -2. No. But then okay, yeah, so if we change this to 2. Okay, sorry, I kind of just made this counterexample up, but you can see that if this is obviously a non-zero determinant because it's going to be 8, but then if we add this together, or honestly this could be 2 or 3 or whatever, this entry here could be 3, but once you add these together you get something like -3, 0, 0, 1. That's a plus b, and that will give you a negative determinant, so the statement is false. I don't know, sometimes it just helps to try numbers, and sometimes things work and sometimes they don't, so in this case I feel like if your intuition tells you that this doesn't really make sense, then trying some numbers could prove you right. Okay, so for C, if A and B are two n-by-n matrices such that AB equals 0, then A and B are singular. So remember that singular means that it's not invertible, which means that you have one of the properties of an invertible matrix is that the determinant of it is not equal to 0. But in the case that it's singular, then the determinant of something must equal 0. So this is claiming that because AB equals 0, that the determinant of A equals 0 and the determinant of B equals 0. Which, again, based on my intuition, that seems a bit strange because, right, if you have AB equals 0, you could have some non-zero. So pretend like these are scalars, right? If you just have A times B equals 0, you can have B equals 0, and then A could be anything. So it doesn't need to be that both have to be 0. So, for example, I guess one way you could approach this is do determinant times AB. We know this is equal determinant of A times determinant of B equals 0. So you can see that the determinant of B could be 0, but the determinant of A could be non-zero, which means that it would be invertible because it's also an n-by-n matrix. So in this case, this is a false statement because you can have one of them being 0, but you don't need to have both being 0. And again, if you want to go the counterexample route, we can say that a non-singular matrix, right? 1, 0, 0, 0. That's a singular matrix, but then you can have a non-singular matrix. So AB needs to be 0, okay. Well, okay, then you can just have a matrix that's 0, 0, 0, 0 times 1, 0, 0, 1, or something random here, it doesn't really matter. But in this case, you can see that you can have an invertible matrix here where the determinant is not equal to 0 and still get AB equals 0. So again, this statement is false. On part D, you have the rows of an n-by-n matrix are linearly independent. The determinant of the transpose times A is greater than 0. So first clue is that determinant, so A is linearly, the rows of A are linearly independent, which means that it's invertible because it's also an n-by-n matrix. And this means because it's invertible, that the determinant of A is not equal to 0. And then we can apply our rules about the determinant that we show here, this part, to see that the determinant of A times the determinant of A transpose is going to be, this is what the statement is claiming. So the other thing to notice here is that the determinant of A will be equal to the determinant of A transpose. And I'm pretty sure the reason for this is that it depends on how you do the cofactor expansion, but if you do the cofactor expansion, you can still get the same determinant or expression. At least for, I think you can prove this pretty simply for a 2x2 matrix, but I won't go into that right now. But this is a property that holds for transposes. Because of that, expression is basically a determinant of a squared, which is always going to be greater than 0, as long as the determinant of a is not 0. But we've already stated that it's not going to be 0 because it's given that this matrix A has linearly independent rows. So this means that this statement is true because the determinant of A is not equal to 0, so that squared will be always greater than 0. So this is the answer. For part E, we have if A is an n by n matrix with A squared equals identity matrix, then determinant of A equals 1. When I was doing this actually confused me for a long time, but then I realized you can again mess around with negatives, and that helped me produce a counterexample, I guess. Because originally I was thinking, 1001, 1001 is fine, but then trying to do with negatives, we still get the same thing. But then I realized you could just have one negative, so something like this, right? So this is also equal to the identity matrix because you have 1, and then here the negative 1 squared to get 1 as well. But in this case, the determinant is going to be negative 1. So it doesn't always have to be equal to 1. So this is a good counterexample where A is equal to 1, 0, 0, negative 1. And that means that this statement is false. Okay, so in this case, we have A equals this matrix, and we're trying to find the inverse, a specific point on the inverse. So from Cramer's rule, you have that the inverse of A, the I and jth entry, is going to be equal to 1 over the determinant of A times negative 1 times I plus j times the determinant of A times j, the A ji, where this matrix is the matrix when you delete row j and column I. Okay, so in this case, we're trying to find A inverse 1, 2. So first we need to find the determinant of A. So I'll just do cofactor expansion along this row. So this means, and remember the checkerboard, so we have 1 times 6, 3, 8, 10, right, deleting the row and column of the entry. And then minus, because it's an alternating checkerboard, right, that I talked about earlier. So minus 2 times 2 times 2, 3, 3, 10, plus 6, and 2, 6, 3, 8. Yeah, okay, so we can do this 60 minus 24 is, no, that's wrong, 36. Minus 2 times 11 plus 6 times negative 2. Yeah, okay. And this gives us 36 minus 22 minus 12, which is 2. So the determinant of A is 2. Okay, so 1 over 2 times negative 1 to the 1 plus 2, which is negative 1. And the determinant, when we delete the second row, and first column, which is this. So then that's 2, 6, 8, and 10, which gives us 20 minus 48, which is negative 28. And this gives us 14. So this is going to be the entry at the first row and second column of the inverse of A, which is our answer. Okay, so in this case, we have V1 and V2 and X, and then B, so is a basis for the span of these values. Okay, what? Sorry. So we have these two vectors and some X value and the basis being the span of V1 and V2. And we're trying to find out if X is in H and to find the coordinate vector of X relative to B. So to first find out if X is in H, we're trying to find if there's a linear combination C1 V1 plus C2 V2 that can give us X. And if you think about it, this is just, if we wanted to multiply it out, this means that C1 minus 2 times C2, and then 2C1 minus 3C 2C1 minus 3C2, then 5C1 plus C2, and then we want this to be equal to -4, -5, 13. So this is just another way of writing this system of equations. So we're going to write this in matrix form. So we have 1, -2, -4, -5, 13, 2, -3, 5, 1. Okay, so now we just want to row reduce this to figure out what C1 and C2 are. I guess another clear way of writing this is saying 1, -2, 2, -3, 5, 1 times C1, C2 equals X, which is -4, -5, 13. And we want to figure out what C1 and C2 are. And we do that by doing this row reduction. Okay, so to row reduce this, I'm going to do R2 equals R2 minus 2R1 first, and that gives us 0, 1, 3. And I'll just keep this row. And then I'm going to do row 3 is equal to row 3 minus 5 times R1, which is 0, 11, 33. Okay. Now we can redo this further. So obviously this is a multiple, this row is a multiple of this row, so we can just make this be a 0, right? We can just say R3 minus 11 R2. So now we have 0, 1, 3. And then what I want to do after that is row 1 is equal to row 1 plus 2 row 2 to get rid of this term. So 1, 0, -4 plus 6 is 2. Okay, so I forgot to put this down here, but now you can see that we have a solution. So C1 equals 2, and C2 equals 3. And so we want to find, so yes, X is in H, and to find the coordinate vector of X relative to B, that means that our coordinate system is we're trying to find the coordinates of V1 along V1 and V2, because we're trying to find it relative to this basis. So this means, get right, that X is equal to C1 times V1 plus C2 times V2. And this is kind of written already quite nicely in the basis of B. So we can see that X written in this basis is just equal to C1, C2, which is 2, 3. So E is our answer. Okay, so in this problem we have a transformation from the R2 vector space to the R3 vector space, and this is a linear transformation, and we're given the results of the transformation where this is the original vector, then after the transformation we have this vector, and same thing for this. And so in part 1 we want to find the standard matrix of T. So the standard matrix refers to the matrix where your columns will be the transformation of your linear basis. So let me just write that down. Oops. So matrix with columns being the transformation of your linear basis. So in this case your linear basis would be 1, 0 and 0, 1. Okay, and also because this is a linear transformation, we have linearity properties, right? So we can write this transformation as AX equals B, where B is the resulting vector in the R3 vector space. And so remember that because it's a linear transformation, if we have the transformation on some vector x1 plus a transformation on a vector x2, that will equal the transformation of the vector x1 plus x2. 2. Okay, and and this makes sense, right? Because this is just doing a times x1 plus a times x2, and then you can just factor out the a and get a times x1 plus x2. So anyways, that was a long-winded explanation about what this transformation means, but from that we can figure out what the basis, the transformation of the basis will be. So in this case, we have the transformation, we want to find the transformation of, say, 1, 0, and okay, actually I want to do 0, 1 first because it's just a bit easier. 0, 1. So, right, this is kind of like our linear combination of 1, 1 and 1, 2. So I want to find a way to get 0, 1 from that. So we can write this as the transformation of 1, 2 minus the transformation of 1, 1. And that gives us, right, because this minus this vector minus this vector gives us just transformation of 0, 1. So when we do that, we get 1, 0, 2, because that's given from up here, minus 3, 2, 1, which gives us negative 2, negative 2, and 1. Okay, so this is for 0, 1, and now you want to find the same, but for 1, 0. And now that we know the transformation of 0, 1 is equal to this, we can just find 1, 0 by doing transformation of 1, 1 minus the transformation of 0, 1. And that will give us 3, 2, 1 minus negative 2, negative 2, 1. And when we do that, we can get 5, 4, 0. And so our standard matrix is then going to be this and this, these two vectors. So we write that as where our first column is going to be the 1, 0, and the second column is going to be 0, 1. So our standard matrix is 5, 4, 0, negative 2, negative 2, 1. So that's equal to, I'll just call it A, because that's what we're kind of referring to with the transformation here, AX equals B. If we want to check your answer, which is always a good thing, you can check that a times 4 negative 2 0 a times 1 1 equals 3 2 1. So when we do that, this is in fact 3 2 1, right? Because we're just checking if this works. And we can do the exact same thing with this one, which I'm not going to do, but you can just double check that to make sure that your standard matrix is correct. Now I want to find the image of the vector u, and that's just saying we want to find the resultants from the transformation. This means that we need to do our ax equals b, where in this case our x is u, and that's 5, negative 2, 4, negative 2, 0, 1 times 1, 3, and that will give us negative 1, negative 2, 3. So that's the image of this u vector. And then finally we're asked if this vector b is in the range of t. So when it's asking the range of the transformation, we want to figure out, is this vector in the span of t? Okay, so we want to determine if there is a vector, let's say, so we have ax equals b, okay, where this is x, this is a, and we're trying to find, is there some x vector which will give us the b vector. So our a vector is 5, negative 2, 4, negative 2, 0, 1. And so we can write this instead now in matrix, our augmented matrix form, where we have 5, negative 2, 4, negative 2, 0, negative 2, 5, 0, 1. And now we just do row reduction to figure out what our x1 and x2 would be, and to see if this gives us a solution. So you can row reduce, and that's pretty standard by this point in the exam. So do row 1 equals row 1 minus row 2, and then after so I'll do this one first, and then that will give me 1, 0, 2, and then I'm going to I'll keep the third row the same, and then after that I'm going to do row 2 equals row 2 minus minus 4 times row 1, and this row 1, right, this now corresponds to this row. It's because I'm doing it after this row operation. This gives me 0, negative 2, negative 10. And then I'm going to divide the second row. Well, first of all, you can see that these two rows are linear combinations of each other. So one of these is going to be zeros, all zeros. And then the other one is just going to be 0, 1, 5, and then 1, 0, 2. So for this one, then we've solved it, so x1 equals 2, and then x2 equals 5. This is fine because there's no inconsistency, so we don't have something like 0, 0, like 2 or something. Because we don't have that, it's valid. We have a valid solution, and this means that it is in the vector, or b is in the vector of t, and the vector x is 2 and 5. And once again, you can check this by literally doing ax and seeing if it equals 0, negative 2, 5, just to check your row reduction. But this is our answer for 8. Yeah, and so when it says find all the vectors x, if this was, well, if you had maybe like 2 rows of zeros, that means you have one free variable. Like, obviously this is not what we got, but if you, for example, did have this, you would have infinitely many solutions, so you wouldn't have just one vector x, but that's not the case in this problem. So just be careful of the wording, because that's in a situation, if you have more than one vector x, that's in a situation where you have maybe infinitely many solutions. But in this case, because we have a single value for each variable, we have only one solution for x. Okay, so in this problem we have this linear system, and we're trying to find a row echelon form for the augmented matrix of the system. So first of all, row echelon form is when you have a matrix with any rows of zeros all at the bottom, and then also if you have, say this is a leading entry or like a non-zero, your leftmost non-zero entry, if you have something, a leading entry here, then in the subsequent rows you need to have the leading entry be to the right, be in the column to the right of the leading entry in the row above it. So for example, if our leading entry is here, then, and this is a 3x3 matrix, then for the second row our leading entry could be here or here. And if our leading entry is here, then this needs to be at 0 and this needs to be 0. So this is a requirement of a row echelon form. So obviously, as you can imagine, there's a lot of different possible forms for this system. Secondly, we want to find the augmented matrix of the system, and so I think I get confused sometimes when I see this, see a system equation sometimes, and I can forget how to organize the terms, I guess. So for example, whenever I get confused, I just write it out like this because I think it's helpful to see the actual multiplication. So if we have, for example, 1, 2, 3 here, then this matches up with the first equation because we get x plus 2y plus 3z from the matrix equals 2. So now I know what to order the matrix in, so I can write it like this. And then to get the augmented matrix, I'm just going to remove this part to write it as a single matrix. In this case, I'll put a dividing bar just so I can figure out what's on the other side of the equal sign. And then from here, it's just row reduction. So I'm going to do the third row is equal to the third row minus 2 times the first row. And that gives me 0, 1, a squared minus 6, and then a minus 7. Yeah. And then this is still 1, 2, 3, 2, 0, 1, a, -4. This is not in row echelon form yet, right? Because our leading entry in this row is not to the right of this entry. So we can keep reducing to get, I'll do row 3 is equal to row 3 minus row 2. Because our ultimate goal is to isolate, I guess I'm skipping a little bit, but in these future problems, we kind of want to isolate the A so that we can figure out what conditions it gives certain solutions. So I'm just going to do this for the third row. So 1 minus 1 is 0, then I get a squared minus a minus 6, and then a minus 3. And so this is a row echelon form for the augmented matrix of the system because, as you can see, we don't have a row of zeros, so obviously that condition is already satisfied. But our leading entries, this leading entry is to the right of this leading entry, and this leading entry is to the right of this leading entry, so everything works out. And your leading entries for row echelon form don't have to be 1 in this situation. Okay, so for part 2, we have for what values of A does the system have an infinite number of solutions. So there's an infinite number of solutions. That means that one of your variables, like x, y, or z, can be anything. So you can have a row of all zeros, basically, right? Because you can see that the first 2 rows here have you will be able to solve for, x or y, but then your last one, z, could be a row of zeros. So we can factor a squared minus a minus 6 into a minus 3 times a plus 2. And we want that to equal 0. But if we want to have an infinite number of solutions, this term needs to also be 0, because otherwise you can't have if you have a row of zeros and then you have a non-zero term here, that's just that's no solution, which is actually this next problem, but I'm getting ahead of myself. So in this case, we want to have a squared minus a minus 6 equal a minus 3, and all of that is equal to 0. So with this one, we have a could be 3 or negative 2. But if a is negative 2, then this is not equal to 0. So that means that when a is equal to 3, a minus 3, this here, and a squared minus a minus 6 are both equal to 0. So that's its value when the system has an infinite number of solutions. If there has no solution, then it's the opposite. Well, not opposite, but you have a squared minus a minus 6 equals 0. But then a minus 3 is not equal to 0. So this gives a equals 3, negative 2, like before. And if a is 3, then a minus 3 won't be 0, or it will be 0. So that means that we want a to be not 3. So the values of a where this doesn't have a solution is when a is equal to negative 2. Okay. And then for last one, for what value of a does this system have a unique solution? So if it has a unique solution, that means that, you're going to have some value here, and there's going to be, some value here that works. That is just, it can be any number, basically. But the point is you want this term to be non-zero. Oh, it's non-zero. And that means that a squared minus a minus 6 cannot be equal to 0. Now we've already established that this equals 0 when a is equal to 3 or negative 2. So when a is not equal to 3 or negative 2, you're going to get a unique solution because this term right here will be non-zero. And so we will be able to have a solution. Yeah, so those are our answers for 9. And now we can go to 10, and now we're trying to find the reduced row echelon form. So the difference between a reduced and just normal row echelon form is that for a reduced one, your leading entries should be 1s. So we're going to have to do more row reduction. So, okay, I'm not going to rewrite this entire matrix out. I'll just start from up here. Okay, so the first thing I'm going to do is try to make these entries 0. So I'm going to do row 3 equals row 3 minus 3 times row 1. I'm going to do the same for row 2 except minus 2 times row 1. And 1, 2, 0, negative 1, 2. And then this will be 0, negative 1, 1, negative 1, row 2, okay, 3, and then the bottom will be 0, negative 2, 1, 0, and 3. Okay, and then what I want to do now is now I want to get rid of this term to make that one a 0, so I can get the reduced row echelon form. So I'll do row 3 equals row 3 minus 2 R2. And then I also want to get rid of this term. Oh yeah, the other thing about reduced row echelon form is you want, in those leading entry columns, I forgot about this, but in those leading entry columns, you want to have, first of all, you want them to be 1s, but then all the other entries in that column should be equal to 0. So that's another thing to remember. Okay, where was it? Okay, so now we have, when we do that, we get 0, 0, -1, 2, -3. And then I'm also going to try to make this entry 0. So I'll do that by doing row 1 equals row 1 plus row 3. Okay, so I did this a bit out of order. So I'm going to first do this and then do this. So row 1 equals row 1 plus row 3 is meaning I'm going to add this row to this row, these two rows together. And that's going to give me 1, 0, 1, -1, 5. And then I'm going to do this row 3 equals row 3 minus 2 times row 2. And then that's going to give me this row, this new R3. So sorry, that was a bit confusing. So now I have 0, -1, 1, -1, 3. Okay, so what I'm going to do first is I'm going to negate row 2 so that there's a positive 1 in the leading entry. And then that gives me 1, 0, 1, -1, 5, 0, 1, -1, 1, -3. And then I'm also going to negate the third row, so I also get a 1 in the leading entry. So I get 0, 0, 1, -2, 3. And then I see now that these are my leading entries, but I want to get these other two entries to be 0 to get it in reduced row echelon form. So to do that, I'm gonna do row 2 equals row 2 plus row 3, and then row 1 equals row 1 minus row 3. Now I get 1, 0, 0, 1, 2, and for row 2 I get 0, 1, 0, -1, 0, and then 0, 0, 1, -2, 3. Okay, so now you can say that we've reached reduced row echelon form because our leading entries are all 1s and they're all to the right of the leading entry in the row before that. And these leading, did I say they're all 1s? But anyways, the columns that the leading entries are in have all their other entries being 0, and then once again the leading entries are all 1s. So we know that we're in reduced row echelon form, and then we don't have any 0 rows, so there's nothing to check there, but that is another requirement if you do have a 0 row. Okay, so now we want to find the basis for the null space of A, and to do this, remember that the null space is the situation when you have AX equals 0. And the basis of the null space of A will be all the spanning vectors that satisfy this equation. So for example, I'm going to assign this x1, x2, x3, x4. So these are the variables, right? Because if we had some vector here, your x1, 2, 3, 4, 5, that would allow for matrix multiplication to happen. So that's why we can determine these 5 variables. But if you have this augmented matrix and then I include the equals to 0 basically, so I have this here, right? If I wanted to solve for x1, x2, x3, x4, x5, then I'm going to assign these 2 free variables because there are no leading entries for these 2 columns. So for example, I'll assign as the parameter s or t and s respectively. If I want to now write this as in terms of the solution for this system, so x1, 2, 3, 4, and 5, I can solve this by moving this term over to the other side. So moving these 2 terms, right? Because what this augmented matrix form tells us is that if I were to actually write, maybe I should have kept this, but if I were to write this times x1, x2, x3, here, okay, let me write this a bit clearer. So if I do have something like this, and then I have this equals to 0, 0, 0, 0, 0. Wait, I'm not giving me, I only need 3 zeros. Yeah, okay. Basically, what these equations will tell us is if we multiply this out, these equations will tell us x1 plus x4 plus 2x5 equals 0. And so if we wanted to so I'm looking at the first row here, just multiplying this one out. So obviously if I wanted to write in terms of these free parameters x1, I can rearrange and just get negative x4 minus 2x5. So that's what I'm going to do down here, but just in matrix form. So I have t plus s, as these are all my only free variables. And x1 is negative x4 minus x5. So I assigned x4 to have the parameter t. So that's negative 1 here, and then negative 2 for x5, which I've assigned the parameter s. And then for x2, the same thing happens, right? I'm going to move this to the other side, so that means I have 1 times t plus 0 times s, because there's 0 here. And then I'll do the same for x3, which gives me 2 and negative 3. And then for x4 is t, so that just means x4 equals t, and then plus 0s. Then same thing for x5, but it's only s and no t. So this is a description of the solution for the null space. And the basis will then be these spanning vectors. So our basis is negative 1, 1, 2, 1, 0, and negative 2, 0, negative 3, 0, 1. And these are the vectors that will span the null space of A. And hopefully you can see this also if you actually multiply all these out. If the matrix form is a little confusing, then if you multiply this out, you'll just get a system of equations that corresponds to multiplying this out. So hopefully that makes sense as to how we find the basis of the null space. And I think that's it. So yeah.